So can everybody hear me? Okay, so I'm Yuval Shagam. I'm a postdoc with Juni and Eric Cornell. And I'd also like to thank, of course, the organizers for inviting me to give this talk. And today I'm going to tell you about the second generation measurement of that we're planning to do on the EDM with trapped molecular ions. And basically, the talk is going to be about the state preparation and the readout that we have revamped in this version, or SPAM, or SPAR, I guess, in this case. So, since we already heard a very short introduction from Dave DeMille and an even faster motivation from Nick Hutzler, I'm going to try to go even faster about the motivation here. And basically, we have some mysteries in our universe, namely the matter-antimatter asymmetry. And there's just not enough CP symmetry violation in the standard model to explain them. And so we've created some extensions to the standard model which have much more CP violation. And these, this CP violation can also manifest itself as a permanent dipole moment for elementary particles such as the electron. And so by measuring this, this quantity very precisely, we're actually able to constrain some of these extensions to the standard model. And here you see our measurement at 10 to the minus 28 charge centimeters, which is about a factor of 12 worse than the best measurement in the world that was done right here at Harvard and within the Harvard-Yale collaboration in the ACME 2 paper, which is about, as I said, a factor of 12 better. So that gives you some motivation about measuring these things. So how would we measure it? Well, if we had a bare electron, well, we would want to apply a magnetic field, and we would be able to do a spin resonance measurement on it and see a frequency. If this electron also had a dipole moment and we applied an electric field to it, the line would shift to one side. And if we flip the direction of the electric field, the line would shift to the other side. And we could measure these two frequencies, and from their difference, we would be able to extract the EDM. So naturally, we want this electric field to be as large as possible so that we can separate these two lines as much as possible. And we want the coherence time to be also very long, because this allows us to see these lines as very narrow objects. And we also would like to have a lot of statistics, and a lot of statistics would help us find the exact center point of these Gaussians very accurately. So the optimal figure of merit at the shot noise limit ends up scaling inversely with the effective electric field applied to this electron, and with a coherence time n as 1 over the square root of the number. And this is going to follow us throughout the talk. So why should we use molecules? Well, we already had plenty of motivation for this, and it's because through relativistic enhancement of specific molecules, we can get effective electric fields that are in the order of tens of gigavolts per centimeter, which is much larger than anything that we can create in the lab. And this is all when we apply a very modest electric field to them. But why should we use molecular ions in this case? Well, I think James gave us a clue about this when he said that they're easy to trap. We've been trapping molecular ions, or well, ions in general, for some decades now. And so if we have a very narrow transition, we would be able to probe it for very long times and get access to long coherence times. In our case, in hafnium fluoride, it's going to be as long as 3 seconds. So if we compare some of the recent measurements of the EDM from different experiments, we see in the top rows, we see beam experiments, which are limited to a certain distance due to the speed of the molecular beam. And so you see coherence times of a few milliseconds. And we're doing extremely well in our last measurement at many hundreds of milliseconds, and we're going to improve on that in this measurement. So you must be thinking, well, we should be killing it in our measurement. But as you can see, we're not. We're well behind the best measurement in the world. And the reason is, you can see it from the next column, where we're getting completely blown out of the water in the number department. And I think the number 10 over here is also pretty optimistic. It's more like 7. So we're going to try and work at improving this thing. And I also, at this point, want to mention some of the other experiments that are warming up with the triatomic measurements. And we also heard from Rick about the barium fluoride measurements. And Amar Vutha is going to do a measurement also of molecules in a crystal, I believe. So since James already showed you our experimental setup in his first slide, I'm just going to jump into the level diagram. So we started with a cold molecular beam of hafnium fluorides, neutrals, and we use near threshold REMP ionization to ionize them so that they wind up in the ground state of hafnium fluoride plus in a few different rotational states. We then stop these molecular ions and begin trapping them in our trap. We then use a 2-photon Raman transition to transfer these molecules into the triple delta 1 state, which has this omega doubling or co-magnetometer effect that we'll talk about, that we already heard about yesterday. And this is going to be the state that's going to have the EDM sensitivity that we're going to use, mainly because it has a very low magnetic dipole moment. So let's zoom on this state. And if there's no electric field applied, we see that we have these lambda doublet states in here, and we're just going to ignore these 2 states in the middle because they only play a secondary role, and we're just going to call these the spin up and spin down states. So if we apply an electric field to these states, well, we can begin mixing these 2 parity states and creating states of good orientation of the molecule. So the top 2 states we're going to call the upper doublet, where the molecule is oriented in one direction, and in the bottom 2 states, it's going to be oriented in the other direction. And we're going to use this as I think Dave DeMille proposed as our 2 co-magnetometer states for the measurement. Now, I'm sure there's someone in the back that's saying, well, didn't you say this is an ion? How are you applying an electric field to an ion? Shouldn't it be flying away? And it's true. Ions are amazing at finding the region with 0 field. And the way that we do it, so if we were to apply an electric field to it, the ion would most likely fly out of the trap, even for a modest electric field. So the way that we do it is we apply an electric field that's rotating just fast enough so that the molecule cannot escape from our trap. So everything is done in a rotating frame of reference, and this also introduces some couplings between the different hyperfine states. So now I've added this E-rot subscript up here, so now you know what that is. So if we apply a magnetic field to this, the spin-up states are going to shift up, and the spin-down states are going to shift down, of course. And we're going to be able to measure these 2 frequencies. Now, we need to remember that the effective electric field that's applied to the electron is going to be oriented with the orientation of the molecule. So it'll be in opposite directions in the upper doublet and in the lower doublet. And then the electron, EDM, is going to be oriented with the spin. So it's going to be oriented in opposite directions in the spin up and spin down case. So effectively, this causes the 2 states in the upper doublet to move slightly further apart, and the 2 states in the lower doublet to move closer together. Well, depending on the sign of the EDM, which we don't know. So far, it's consistent with 0. And so if we were to measure the energy difference between the upper 2 doublets and the lower 2 doublets and take the difference of that, we should be able to extract the EDM from it. So how do we do our measurement? Well, we begin by creating our ions and preparing them in a single one of these 4 states. We then apply our pi/2 pulses and let the system spin precess. And when we stop, we may find them in an equal number in the 2 spin up and spin down states. We then project our state by kicking out one of these spin states into Hilbert space. And then we proceed to dissociate our molecule, this entire state selectively, and kick it out onto the MCP, and then we can detect the hafnium photofragment by time of flight mass spectrometry, and the number of hafniums that we'll count will be basically proportional to the number that were actually in the state. And so we can do this for both of these spin up and spin down states, and for the upper doublet, and we can extract Ramsey fringes that look something like this with a coherence time of around 700 milliseconds. And so up until now, there hasn't been really anything new with this. But as I said before, we really want to improve the ion number, the count rate that we have in the experiment. And for this, we built a much bigger trap with much more uniform fields so that we can trap the ions in a much larger volume while we apply an electric field to them. And also, we revamped our electronics to be able to apply a much stronger polarizing electric field. And this helps us keep down some Berry phase effects that cause us to dephase through collisions between ions. And the other thing that we had to do is, now that our count rate was about a factor of 20 or 30 or I think even 50 higher, is we had to switch to counting our ions by imaging, where instead of counting them in time of flight, we would see spots for the individual ions and we would be able to count the number of spots. And the reason I'm showing this is because this is going to allude to something that I'm going to get to later in the talk, that you see that the ions are actually breaking up into an interesting spatial pattern that looks like two blobs. So the immediate gain from these improvements can be seen here. So this is the old fringe, and this is our what our new fringe looks like. So the first thing that you notice is that our coherence time is much longer. It's in this fringe, it's about 2.4 seconds. The second thing that you notice is that the error bars on these points are much, much smaller. And this is even though we're using a very similar number of shots to measure this. And this is, of course, a result of the much higher count rate. And basically, these improvements lead us to an improvement where before, if we had about a millihertz precision in 200 hours, now we can achieve the same precision in 3.2 hours. But the question is this enough? And the problem is that to really use these co-magnetometer states efficiently, you really want to be able to switch between the upper doublet and lower doublet as quickly as you can. And we're measuring one state at a time. And of course, this rate is going to go down as we increase our coherence time. And so we'll be very susceptible to drifts in the magnetic field between the two measurements that we make. And the second issue that we have is that we are using photodissociation and action spectroscopy technique to detect these molecules. And that's very good because you can detect ions at the end of the day with very, very high quantum efficiency. But these kinds of action spectroscopy techniques usually carry with them very high fractional noise on our system, fractional technical noise. And this is due to them being very spectrally broad and very non-uniform in their power in a shot-to-shot basis. And in our system, we found that our noise actually scales as about 15% of the signal that we have in the system. So for 500 ions, this comes out to about 3 times shot noise. And you may say, okay, it's only 3 times shot noise. Well, that's 10 times as much data. So that's a really big deal to average down for 10 times as long for us. And so we really want to be able to beat this limit. And sure, you could think about seeding your pulsed dye laser and making it spectrally narrow, and think about correlating its power and trying to reduce this noise. But let's think about another idea. What if we were to be able to measure both of these doublets simultaneously? What would happen if we were to be able to measure both of these states at the same time? Well, before that, our noise would be uncorrelated. So if you were sitting on the side of the fringe, while one shot would be jumping up, the other shot would be jumping down. And this asymmetry that we're calculating here is going to be proportional to the number that we count in a spin up or spin down state, depending on the sign that you choose in there. But if we measure both of the doublets from the same dissociation shots, then this technical noise should be common mode. Both of these fringes would jump up at the same time. And if you remember from before, I mentioned that we're actually only interested in the difference between these two fringes. And so we could subtract these two signals and feed the beat frequency, which should be much lower in noise. The second thing that you notice is that if there is any phase noise that on this fringe, on where we're sitting, it's going to also manifest as an amplitude noise that's going to be common mode. So if we move the phase off in one direction, the number is going to seem as if it's gone up. And so this should also be common mode for these two measurements. So we now have a lot of motivation on why to do this. So now it's all simple. We need to do spam. We need to be able to prepare this state, and we need to be able to detect it simultaneously. So how do we do that? Well, before I mentioned that we were using this off-resonant Raman transition to transfer our ions into either the upper doublet or the lower doublet of this triple delta 1 state. Well, there's an old trick in the AMO bag of tools, I think, that's known as optical pumping. What if we were to just move this laser onto resonance and choose an electronic state that has a favorable branching ratio into the triple delta 1 state, and we can also couple all of these rotational states with microwaves fairly easily, and we would be able to get all these molecules to move over into the triple delta 1 state. Okay, that's one step. Now we can apply a second laser on an electronic transition that actually likes to cycle over here. Not so much because of the Frank-Condon factors, but pretty good. And if we apply this with circular polarization, we can move these molecules into the fully stretched state. So that's great. We've created our ions in the spin-up state. That was easy. We had two lasers before, and we have two lasers now. So I guess the conclusion is that molecules are simple. We've cooled our molecules into two quantum states. I don't know why June is complaining about YO being so difficult to laser cool. Well, there's a reason. And the reason is that there are all these different vibrational states and rotational states over here where our molecules could disappear into Hilbert space. And actually, I'm like, if we zoom in, it looks like this if you add the hyperfine structure and the parity structure into it. Well, if we choose our transitions to be in a wise way, depending on the different rotational lines, and we also add two lasers over here to clean up anything that would come back. So if you have a 2-second coherence time, yeah, everything that disappeared into Hilbert space is going to come back and hurt you later on. Well, we can solve this problem. And I'm going to half ask you to trust me on this for now because I want to move on. So we've now managed to prepare a single spin state in both doublets, and we can apply our pi/2 pulses to it and measure and have a fringe appear in both of these. But we still need to be able to detect these two states independently. And the problem here is that we were using two-photon dissociation before, and we were going through a state that had no orientation. And so even though our molecule had a good orientation here, this orientation would disappear in the intermediate state, and it would come out completely mixed. So we did some spectroscopy with the help of Tanya Zelevinsky. We found that if we have an oriented intermediate state, our photo fragments are going to be oriented in space. And what this results in is one of these doublets appears on one side of our detector, and the other doublet appears on the other side of the detector. And I'm a little bit embarrassed that these aren't as beautiful as the pictures that Robert showed us before that Tanya took, but I think they're pretty good for us. And there's a tiny bit of overlap that I won't get into yet. And there's one more thing that I've been hiding from you so far, and that's that the G factor is actually not exactly the same in the upper doublet and in the lower doublet. So that means that we're going to be measuring two different frequencies on the left side of our detector and on the right side of the detector. And so if we look at our resulting Ramsey fringe, we see that at early time they are both in phase, and at about 750 milliseconds they go out of phase, coming back into phase at 1.5 seconds in this case. And okay, that's pretty good. That's looks like a good Ramsey fringe. We've succeeded in our span. So how does this help us? Well, if we were to naively look at our error bars on each individual fringe separately, well, we would see that we would find that our standard deviation on these points corresponds to these blue lines, which is well above the shot noise limit, which is the quantum projection noise limit, which is depicted by the dashed lines that you see all the way down here. But we know that we don't have to take our standard deviation this way. We're actually only interested in the differences. So if for each individual point, we are first to take the difference between the 2 points, we would find that our standard deviation is now much lower and pretty much at the quantum projection noise limit. And we're fairly certain that we know what limits us from hitting the quantum projection noise limit, and we can, on a given day, make it better and have it really reach the quantum projection noise limit. So you notice that I didn't show you what's going on here in the out-of-phase measurements. Well, let's think about it first. What will happen in the out-of-phase measurement? Well, if we have number noise, the numbers going up and down, that's going to be common mode even when we're out of phase. But if we have any sort of phase noise on this, it's actually going to manifest itself as an opposite direction number noise. And so the noise would not cancel in this case. So if we look at the results, yeah, we see that we are well above the quantum projection noise limit. There is some technical noise cancellation here, but we're still well above it. But this also alludes to us, if we measure our EDM signal when we're back in phase, this is a noise that should cancel and we wouldn't have to deal with. And this tells you how much noise we wouldn't have to deal with just by taking our measurements when the two doublets are back in phase. And so, how am I doing on time? Great. Oh, I went fast. Okay. So, basically, the point of all of this is that, well, we could only achieve two-state detection in our system. And this actually turns out to be almost as good as four-state detection. If we had four-state detection, we would be able to detect our EDM signal at any time. But this puts a little bit of a constraint on us where we have to wait for the fringes to be in phase, but that's not so bad. We can tune most of these frequencies and use this two-state detection to be at the quantum projection noise limit. And so if you take a look at our sensitivity today, well, we haven't fully optimized our data taking yet, but it is on the order of a millihertz per root hour. And you can compare this number to the Acme 2 limit at this point and see that it's very comparable. And we hope to be able to improve this a little bit. But we've achieved this by going to 2.4 seconds of coherence time, which is fairly typical in our experiment, although not lately, and we're not sure why. But the ion number has also grown. And the other thing that I didn't talk about is that our contrast has also, our fringe contrast has improved to about 0.8 from 0.6. And if I have more time, well, I'll also mention that Will, who's sitting out in the crowd, will be giving a great poster today. And I guess I'll also mention the next generation of EDM measurements that will use thorium fluoride. And basically, when I showed you this optimal limit to the EDM sensitivity, well, you see that it scales as 1 over the coherence time. And with our next generation molecule of thorium fluoride, where this science state, this triple delta 1 state, is the ground state, we expect to be able to reach, with some cryogenic cooling, coherence times of about 60 seconds. But the actual, the effective sensitivity to the EDM, well, is going to not exactly scale like that, because as we increase our coherence time, if we're using a single trap, our count rate is going to decrease with the coherence time. And so we'll actually only be gaining by the square root of the gain of the coherence time, which isn't a lot. It's about a factor of 5 above this. But we can make another improvement, and really our lasers are pulsing at about 10 hertz. So we have a lot of dead time where we're not using our lasers. So you could think about separating our ion creation and ion detection chambers, and in the middle having a conveyor belt to move our ions from one side to the other. And so we can create these little buckets of ions that are spin processing and taking their sweet time spin processing, and be able to really increase our rep rate and really achieve this optimal case where we expect to see maybe a factor of 50 further gain in sensitivity to the EDM. And so with that, this is a picture of the group. I'd like to thank Eric and June. And so the people working on the hafnium fluoride are Will, Tanya, and Tanner, who are pictured here. Will is giving a poster today. I mentioned that again. This is Tanya, and Tanner is photoshopped into the picture, not very well photoshopped. And we have some past EDMers who are sitting in the crowd, and also some temporary EDMers there. So I'd like to thank you for your attention. Yes.
And have you identified any possible systematic errors due to correlations of the movement of that cut with any of your switches? What we call switches is, just for the whole ions, we call switches as changing something like the direction of the electric field or the orientation of the molecule.
That, of course, is like a super dangerous systematic. If, for example, with our B field switch, the contrast or this cut were to change in any way, and we haven't, this is like the next thing on our list to study at this point. But yeah, we're very worried about that. That's, but we kind of have a feeling that it'll work.
Start in the back.
Yeah, it's very nice that you can detect both states simultaneously, but also from presentation it looks like you only get the contrast from the same quadrature. Do I just switch between the two quadratures of this?
So you're talking about the fact that when we measure these states, we're only measuring the spin down states at the same time and not the spin up states at the same time? Yes. So this is true, and this makes it so that the noise doesn't cancel away, except when these two different fringes are in phase. And so this is why we don't actually need to detect all 4 states at the same time. But of course, 4-state detection would be better.
Yeah, the natural thing about detecting both quadratures simultaneously instead of detecting.
Oh, you're talking about detecting these 2 states at the same time, or the top 2 ones. Yeah. So if we were to, the first thing is that we cannot do that. But if we were able to detect these 2 states, yes, you would get all the technical noise canceling at the same time. But the magnetic field noise would actually not cancel as well. And so it's actually better to to measure the two doublets separately as opposed to measuring only the top states. We were actually confused about this for some time, about how it's actually the same. But it turns out that when you're on the side of the fringe in both of the doublets, well, the population is actually approximately the same, should be approximately the same in all four of these states. And that's why it allows all of these things to come about, where we can cancel everything. It's just because under the approximation that the numbers are the same in all four of these states, we can really spy on these different states with just the two states that we can measure. I don't know if that's clear, but we can talk about it later.
I have two questions. One is a technical, the other one is a general question. The technical question is for this MCP detection. You have so many ions on the MCP. I remember MCP can have a dead time. You can only accept one ion for a fixed time. How do you get around about that? So have so many ions on the MCP.
So for an MCP, right, that dead time is really going to be per pore. So if you spread your ions on a big area on the MCP, you only really have like a local dead time. And we do find that we get close to saturating the MCP, but not with the hafnium signal, which is of about 1,000 ions. We actually saturate the MCP with the roughly 20 or 30,000 hafnium fluorides that arrive right after this. But we've characterized this saturation fairly well, and so we can measure both the hafnium fluorides and the hafniums at the same time. But this is many shots. This isn't a single shot. This is about 20 shots that are averaged down. But you would have about 1,000 to 1,500 ions in a single shot imaged.
Okay. My general question is, for the ACME2 experiment, we use like a fluorescence detection, right? Here is the ionization detection. How do you guys choose these different methods, and which one is the more efficient ones?
So, all right, it's a question of the numbers that you have. I think that, right, here it's a question of like the efficiency of your dissociation. After you dissociate, yes, you can use an MCP to detect with about 80% quantum efficiency the ions that you have. So that is a big plus. But in our case, if we did a calculation for how many photons we can scatter per state, well, we find, and with our collection efficiency and with the quantum efficiency of detectors at the wavelengths that would be required, well, we found that it's absolutely laughable relative to the quantum efficiency that we would get from this method. But in the next generation molecule, we've actually found that we can close up enough vibrational states to cycle as many as 100 photons, possibly. And this could make it feasible to use fluorescence detection on it, although that would still not be, so with fluorescence detection, right, you can switch between your spin up and spin down states very quickly, but it's still not exactly simultaneous. So we're actually quite happy with this photodissociation technique right up until we start looking more into the systematics of it, as John mentioned before.
I have a stupid question. So, I mean, since you're working with these ion clouds, what about the electric fields between? I mean, is that something, since I have no feeling, is that something we can completely neglect?
Between the ions?
Yeah, because that's something determined, like the EROT, it's not the only thing that's going to be there, right, if you're working with these clouds.
Yeah, so that electric field, it comes in from ion-ion collisions, and it really shifts our quantization axis every time there's a collision. And so, yes, this will cause decoherence, and this is why we need such a big trap to be able to trap our ions and make it like the cloud not quite as dense. So right now, if we really crank up our ion number all the way to the limit, yes, you see your coherence time will go down to about a second as opposed to 2.5 seconds. But at the same time, it really makes it important to see that the efficiency is very important, right? You want to, so we start with 20,000 ions, and in the end, about 1,000 of them arrive at our detector. So if we are able to state prepare our molecules more efficiently, then we can put in more molecules in there and be less sensitive to this decoherence, these decoherence effects. And the other thing I guess I should mention about this is that we were able to do this optical pumping and state preparation on a molecule that we chose only due to its sensitivity to the EDN. It's not a molecule that has particularly good diagonal Frank-Condon factors or anything, but it's still possible to use optical pumping to prepare it. And this works a lot more efficiently, about a factor of 3 more efficiently. We're not trying so hard actually to get it really good yet, but it works a lot better than the 2-photon Raman transition that we had before, a lot more efficiently.
All right, great. I think we have to move on, so let's thank the speaker again. Thank you.